So the alternative that I'm going to be showing you is I think if you put a little bit of effort up front to write more accurate declarations, what you'll see is a payback in that then when you go to access the thing you've declared, that those accesses will be much easier and more reliable to do. Next. And so another way to think about this is that when you are declaring the representation of something like a memory map device, that you'll just write those declarations once. And so that's just a one-time act. And if that's a lot more work, but it's only once. But think about how often you go back and talk to that device. You want to send, receive data, test its state, reconfigure it, that sort of thing. That you could potentially do many times. Next. And so what I'm going to be doing is weaving in the advice that I presented in my talk earlier today, just repeating that from this morning, is that I'm telling you make interfaces easy to use correctly and hard to use incorrectly, and couple that with my additional advice that you want to program in a style that turns potential runtime errors into compile time errors. Next. The topic area in particular I'm talking about is dealing with memory map devices. And even if you don't do this kind of work, I hope what you'll find interesting about this is the manner in which I use language to express ideas in an accurate and both accurate and concise way. Next slide, please. So basically, when you're doing memory mapped I/O, you're dealing with an architecture which has these device registers which appear to the instruction set as if they are just ordinary memory locations, in the sense that you use the same instructions with the same addressing modes that you would use to reach physical memory. Let's see if this thing works there. But instead, you're reaching a different portion of the address space, which doesn't contain real memory, but contains the controllers, essentially, for the devices you want to talk to. Next. And I'm going to pick one example and just follow it through in some detail. I've done a fair amount of work with a particular single board computer that has a couple of UART registers on it that it's actually 6 registers that are used in various combinations to get the work done. And so I'm going to be talking about how does one model this. Next. Now, the first thing most people learn to do is to just pick an appropriate integer type. For example, if you want to model a 2-byte register, you would pick something, these days you would include in C standard int.h, and C++ it's C standard int, and you use a type like uint16. In the examples I'm going to be doing, it's all 4-byte words that are 4-byte aligned. uint32t works very well for that. Next. Now, here's conceptually what's very interesting about this is that normally you don't choose where the compiler puts objects. You will write declarations that you will put at global scope or in a namespace or local to a function. And the compiler says, okay, I'll take it from here. I will figure out where to place these objects. I may get some help from the linker, but you don't say, I want this thing to reside at this specific address. Next. But for memory mapped registers, what happens is the hardware has already chosen where those locations are. So you can't use conventional declarations to declare objects. You have to do something else. Next. So a fair number of compilers give you extensions, things that look like this, where you use like underscore at and parentheses or the at sign. And this says, I want to declare this uint32t object at that location. And the compiler will then cooperate with the linker to say, okay, that's the address at which I'm going to put it. But notice that this is non-standard. This is going to vary from compiler to compiler, and some compilers have nothing like this at all. You have to do something else. So let's look at what you can do with the standard. Next. The common C approach is to write a macro declaration like that. I made some reference to that in my talk this morning. Next. The preferred way to do this in C++ is to declare a constant object, and rather than use the old style cast is to use a reinterpret cast. And by the way, I think an easy explanation for what's the Reinterpret Cast do. Basically, a Reinterpret Cast is just like a static cast, except it has implementation-defined behavior. What that means is that the standard doesn't say exactly how it works. It says this is up to each platform to make this work. Now, on most architectures with which we work, in which integers and pointers are the same size, this Reinterpret Cast essentially does nothing. It simply gives compile time permission to take the bit representation of an int and put it into a pointer. Next. But either way, whether you use the macro or whether you use the const object, this is the way you manipulate it. You just dereference the pointer as if it were pointing into memory, store something into it. You've just written something to a UART. Next. Now in C++, I kind of like this alternate notation, using a reference instead of a constant pointer. The curious thing about it, though, is that you can do the Reinterpret Cast. A cast to a reference type has semantics which don't work in this case. What you have to do is cast to a pointer type and then dereference the pointer so that this says, give me the object to which this pointer points, and then you can bind a reference to it. It's a curious little thing that you wind up putting the pointer in front of the result of the cast in order to bind it to the reference. But it works. Next. Once you've set that up, now this memory map device really does look much more like an object. You don't have to put the star in front of it. Next. Now, as I alluded to this morning, this way of doing things, though, is type unsafe, in that if you have all of these individual registers, all being of the same type, it's very easy to have accidents where you get the registers in the wrong order, or next. You inadvertently mix a register from one device and a register from another device, and these are errors that can't be caught at translation time. You get the joy of debugging it. Next. So my recommendation is to cluster them into a structure and then write functions which pass the whole structure. You show up in there, and that function will pick out the registers it needs to do whatever that operation is. It's an easier to use interface, both easy to use correctly and hard to use incorrectly. Next. Now, doing a class is a step up, because what you do is you make the registers private, and that eliminates the ability of the user of UART to go in and screw up the state of these registers. They can only access the registers through operations that are permitted in the public interface. And I think that constraint on behavior does have the benefit of cutting down on spurious errors. Next. But another issue that you have to address is to realize that device registers aren't ordinary memory, in the sense that reads and writes to device registers can have side effects which are invisible to the processor. The act of writing into a transmit buffer initiates interaction with an external device. The compiler doesn't see that. It just sees you just did a write to memory. Next. And so there are a whole bunch of compiler optimizations that you really appreciate when they're being done on ordinary memory, but when they're being done on device registers, if the compiler optimizes the way they access, they will eliminate those side effects, and they'll cause the device software to fail. Next. So that's where volatile comes in. And so it's good practice to declare entities representing memory map devices as volatile. And what I want to do is talk about exactly where you place the volatile, because that has stylistic consequences. Next. So this seems like the obvious thing to do, is to say I've got now a pointer, a constant pointer to a volatile UART. Com1 is a pointer that you can't change. It's always pointing to the same spot, pointing to a UART that has this attribute of being volatile, meaning I'm actually telling the compiler, do not optimize this thing to the point where it doesn't work. If I tell you to write to that register, write to that register. If you think you already wrote to it, do it again. You can't optimize that away. Next. This is the comparable version of the reference declaration. Com1 is a reference to a volatile UART. Next. Now, this is the subtlety, which is that when you write the declaration like this, there is an implication, a non-obvious implication, until you realize, oh yeah, that's what it's saying is, This says that a UART is not volatile in and of itself. It says some UARTs might be volatile and some might not be volatile. And so if you want them to be volatile, every time you declare them, you now have to take the step of adding the volatile. Next. So if you leave it out, I made that kind of feint to convey the ideas. That's where it should be, but it could be left out. Now you're allowing the compiler to do optimizations, which could render the accesses to that thing non-working. And that's an accident that you don't want to allow other people to do. In other words, I'm looking at this from a team perspective. I write a class that models a UART, I give it to other people, and I want to make it easy for them to use correctly and hard to use incorrectly. And mandating that they remember to put the volatile in there is an opportunity for them to use it incorrectly. So the volatility should be built in. Next. So if every UART is volatile, make it part of the type as follows. Here are some, I'm going to show you some failed attempts first, and then show you what I think you should do. Next. One thing you could say is, well, I'll just put it in the type by declaring those registers that are volatile to be volatile and those that are not to be non-volatile. In theory, you say, well, yeah, that's the right way to do it. In practice, this almost never happens. I can't imagine a situation where they're either none of them are volatile or all of them are volatile. It's rare that you have this mixture of volatile and non-volatile things. So we want to make the whole UART type volatile. How might we do that? Next. You could say, okay, I'll just put the word volatile in front of the class declaration. That's a compile error. Why is it a compile error? Well, there are a whole bunch of keywords in C++ which if you put them like extern or static, volatile, const, you put them out here, and it doesn't apply to the class definition. What it does is it's looking for something to be between that curly brace and that semicolon. Next. It's looking for something like that. This doesn't say that UART is volatile. What it says is that U is an object of type UART, which is volatile. The volatility only applies to that one, not to the type. Next. So you could say, I know how to do it. I'll make UART a type def. See, now the volatile applies to that. I've made it a type def, and that works. But if you try this, experiment with this, you say, well, then why do I need to have a class name here? Because I'm going to be just using that. You can have an anonymous class. But this drives the compiler and the linker nuts. You get all kinds of warnings about an anonymous class that has linkage. And so you wind up giving in and say, hey, I really do have a class called NVUART, and I have this type def called UART. That's what I want most people using. But I'm going to use this name for naming the constructors and things like that. Next. So it leads to problems like this. You also wind up declaring every member function volatile. And that becomes tedious. It's just hard to propagate that through and maintain it. Next. So what I find is almost always the best approach is just to go back to here, to this type def, and put the volatility right in there. Make it that every device register is a volatile uint32. Next. And so you wind up just nice, clean, simple. And the volatility is just a part of every one of those members. So although UART itself isn't a volatile type, the net effect is that it behaves like one because every one of its data members is volatile, which is just as good. Simple, clean. I think this is the right way to package volatility into these things. Next. So now you can write, that's how simple your declarations look, like that, like that. Next. Now, here's another pragmatic issue you run into, which is that we have these registers in this order. When I wrote that struct or that class, how do I know, how can I be confident that the storage layout for that class or struct is actually going to match this? Next. And this is a practical problem, which I have often heard people say that I'd write these structures and then I'd compile my code, or it would be working fine, and then I'd port it to another platform or start using a different compiler, and it would do padding and alignment on members and throw everything out of whack, and then I'd have to debug code that I thought was working. So how can we prevent those accidents? Well, The insight comes from understanding there is in C++ this concept called a standard layout type. A standard layout type is a class or structure that is it's missing just enough features so that the compiler can guarantee that the layout will come out right. So what is a standard layout type? Well, basically, it's anything you can write in C. A C structure is any of the primitive types, arrays of standard layout types, and then there's the thing called a standard layout class, which could possibly be declared as a structure or union. Next. And it can contain things that one normally finds in a C++ class. It contains static and non-static data members, as long as all of those are standard layout types. It can contain base classes. You can derive one class from another, and it's still standard layout if the base class is a standard layout type. It can have static and non-virtual member functions, and it can have nested constants and types. And none of these things will disturb the layout guarantee. Next. But what will disturb it is a virtual function, because the compiler will sneak a v pointer somewhere into the layout of the object. And so putting a virtual function turns this into a polymorphic type. Polymorphic types are not standard layout types. Next. Here's another example of something that isn't standard layout. See, the requirement is that all of the members have to have the same access control. They all have to be public, they all have to be private, they all have to be protected. As soon as you have more than one, the compiler has permission to reorder these things. And that destroys the layout guarantee. Next. Here's an example where we have a base class. See, it could be that you want to be able to collect all the registers, the physical layout into a struct, and then you can derive a class from that struct and then put member functions in here. And that'll work as long as you don't add any more data members. The requirement is that all of the members have to be either in the base class, the same base class, or they have to be in the most derived class. But as soon as you divide them up at different levels in the hierarchy, now it's not standard layout anymore. Next. Now, the beauty is that in modern C++, you don't have to guess. You can do a static assertion on this so that you can just take your best shot at writing what you think is standard layout and not worry that, oh, I violated the rules and I didn't know it. You can do a static assertion and there is a type trait. You include the type trait's header and you can say is standard layout on the type, and if it isn't standard layout, then you'll get a compile time error message. Again, this gives you a nice, good feeling that this thing will lay out the way you expect it to. Next. Now, unfortunately, the layout guarantees are a little less meaty than we want them to be. They still allow for opportunities to screw up the alignment. The first guarantee is that the first non-static data member is always at offset 0. There's no padding in front of it. The address of that first member in a standard layout type is the same as the address of the whole object. That's a guarantee. And then there's a guarantee that every other non-static data member is at an offset which is greater than the previous one. So they are in the order in which you wrote them. The thing you have to worry about is there padding in between them? Padding that throws off the alignment. Now, in my examples where everything is a 4-byte word on a 4-byte boundary, the compiler has no incentive to throw extraneous padding in there. I've never seen a problem with that. But if you have registers of different sizes, 1-byte, 2-byte, 4-byte registers, and you're trying to put them in there, now you start to worry about the padding and alignment. Next. So you can, I've already stated that there's none before the first. Next. So our UART type is a standard layout type. There's a guarantee that that first register, ULCON, will be at offset 0. But what about the other offsets? Next. Well, again, compilers provide some non-standard features to control this stuff. There's one example. Next. Here's another. The GNU compiler has an attribute packed. It's not a pragma. But exactly whether the compiler provides this and exactly the form will vary from platform to platform. Next. So if you really have to be sure that everything lines up, you may have to do it this way, which you see that and you say, well, then what's the advantage? Why not just write all those macros that explicitly stated exactly what the offset was? And the answer is because this still has the advantage of giving you a nice abstract type for the entire collection. That when you pass around a UART, you're passing around the whole collection as an abstraction. So this might be a little tedious, but again, you do it once, and then you're pretty much protected against what happens when you recompile, when you port the code. Next.
At what point you have to make this static assertion?
Can you back up one slide, please? Thank you.
Have to be a member of a class?
No, this can just, I typically just put it in the header file where I declare this. I just put these static assertions right after it. Now, you can't put them inside because you can't refer to this until it's a complete type. So you typically do this right afterwards. Now, the offset, this is a standard macro that comes from the C library. It works with structures. It used to be that the advice was you can't use this with classes, but you can use it with a standard layout type. That is specified as OK. Next. And so, yeah, I just mentioned that. Next. And so checking the offset of each individual member is often unnecessary. There may be ways to get around that. Next. Like, for example, this one might work just fine, is that if your expectation is that the UART is just 6 full words, all word aligned, there shouldn't be any padding at all, then the size of the UART should simply be 6 times the size of register. And that one check is a nice way to guarantee there's no padding. Next. Now, in the examples that follow, I just threw in this declaration because I didn't want you wondering where did this come from. It's not at all uncommon that a class which manipulates or it wraps a piece of hardware, there might be bit settings in some of the registers that you want to have part of the interface to the member functions of the class. And so I think an appropriate thing to do is to make that a public enumerated type in this case that defines the various constants and that type. You might have type defs in there or other constants, and it's appropriate to make them part of the public interface. Next. So one thing I haven't addressed yet is what do you do about initializing objects of this type? Well, the convention in C++ is to write constructors. And this, by the way, is another area where I think the response of many C programmers is to be a little bit leery of constructors. It's that they don't know when these things will be called, and they want to have precise control over the timing and the order in which things get initialized. And they feel like, well, if I do it in C++, writing declarations, I don't quite know where the constructors are going to be invoked. And in fact, if you are writing global declarations, things at namespace scope, the C++ standard does not spell out precisely the order in which those, they will tell you that within a given translation unit, the static constructors will run in the order in which the things are declared, but it doesn't specify the order across modules. So you could have the things in one module being initialized before or after the things in another module. And if you want more precise control over that, what can you do? So let's talk about the issues of writing a constructor for a memory map type like this. Next. And by the way, I think the real beauty of using constructors is that they provide what's called guaranteed initialization. It's that if you, as the author of a class, write a constructor for that class, it now becomes the compiler's responsibility to make sure that every time you create an object of that type, it gets constructed. It removes a class of failure to initialize errors. Again, it makes something easy to use correctly and hard to use incorrectly, because now you have a compile time guarantee that it will be constructed. The problem is that a cast can invalidate that guarantee. Next. And that's exactly what we've been doing, is we haven't been defining any objects of the UART type. What we're doing is we're using these reinterpret casts to take an integer value and pretend that it's a pointer. We're pretending that that memory map space is an object, but the constructor doesn't run. So when you use a cast, it fails to generate the code for the constructor, and that's a problem. We want to get the constructor to run. How can we do it? Next. This is the illustration. So again, as I've said before, and I'll say again, casts are dangerous, and yet another reason is they invalidate initialization guarantees. But the way around that is commonly practiced is to use new with placement, which I'll show you the mechanics of it very briefly, and then tell you, but it's not my favorite solution, and I'll show you why. Next. Just a little bit of background. When you write a new expression in C++, a new expression turns around and calls an operator new that does the memory allocation. And operator new receives it's very much like a call on the C function malloc. You give it the number of bytes you want to allocate, and it returns to you a pointer to the storage that it just allocated. Next. And so writing a new expression like that, new t parenthesis v, says make me a new object of type t allocated from the free store and initialize it passing that v as the argument to the constructor. Now, this translates into really a two-step process here. The first one being allocate the storage, the second one being call a constructor. Now that notation right there is not real C++. It's my make-believe placeholder for invoke the constructor on the object pointed to by P, passing it the argument V. The compiler does that for you. Excuse me. Next. There is this variant. It's a standard C++ called new with placement. This is its implementation. It's an operator new. Operator new, like so many other functions, can be overloaded, meaning you can have more than one operator new with different parameter lists. And operator new has a first parameter, which is the size of the thing to allocate. But notice, it has no name for that parameter because it's not being used. It has a second parameter, which is a pointer, which is taken as pointer to storage that is already allocated. And so placement new simply returns whatever pointer comes in, it passes it right back out. Next. And this is how you use it. You write new, and you put the argument to the, effectively the second argument to placement operator new is written here in parentheses between the word new and the type t. So that's the argument to the constructor if required, and that is the argument to the placement new. And the compiler turns around and calls that operator new with placement, passing it, that thing goes there, that type goes in there. This type is ignored, actually, and what this really does is it has the effect of assigning region to P. And then it says apply the constructor to it. So region represents storage that already exists, and what this notation effectively does is it says apply a constructor to storage I've already got. I can use placement new to basically say place the object here, which really just means run the constructor. And when I'm teaching C++ to beginners, one of the things I tell them is that constructors are kind of unique in that you can't call a constructor like it's an ordinary function. There's no notation by which you can say object.constructor. But I'm very careful to say but I don't want to say you can't call a constructor. You just can't call it using the dot or arrow notation. But you can call a constructor using placement new. That's effectively what its job is. So this says place an object of type t initialized with v in that region. Next. So applied to our UART, this is what it looks like. You still do the same reinterpret cast the way you did before. But then you follow it up with a placement new, and that has the effect of running the constructor at the location that you just identified as the memory mapped location of the UART. And it turns out that you're passing it a pointer to a location you already got, and operator new returns the pointer to what it just allocated. What comes out of new is what just went in. This is a situation where you really don't even have to assign it. It looks kind of odd, but it turns out there's no reason to assign it. You've already done it right there, and you're just passing it in to say call the constructor. Next. Now you could fold it all into one expression, but I'm not sure that's an improvement. It challenges readability, possibly. And you can also use the reference notation in place of the pointer notation, but then you have the curious thing that you put a star in front of the Reinterpret Cast in order to accommodate the reference. But all of these different approaches work. But they have a basic problem. They still have the problem that it becomes the user's responsibility to remember to invoke the placement operator new. It leaves the opportunity for an accident. So this is possibly easy to use incorrectly, and we don't want that. Next. And by the way, if you do have a constructor that takes arguments, there's your opportunity to pass it to the UART constructor. Next. So here is a refinement that I like better, which is that C++ lets you declare an operator new as a member of a class. And so that if type T is a class which has a member operator new, you just write a new expression the way you always did, and the compiler will find the operator new that is in the class and use that instead of the global operator new. Next. And so here is the syntax for defining an operator new as a member. And notice that what this does, this basically says that when you allocate the storage for UART, you just take the value of the address that you know it resides at, and you return that as the result of operator new. And this lets you do something very elegant, which looks like this. Next. Right there. You can just say that the COM0 port is a new UART. And that gets the value without making the user know what that magic number was. It just says, wherever that UART is, give me that address and construct it before you give it to me. It looks much more like a conventional operator new. And because it's so conventional, it's hard to screw up. It looks really like just garden variety memory allocation. Next. Now, again, I like the reference notation. I like declaring these things as references instead of as constant pointers. And the consequence, though, is you wind up doing a curious thing with operator new, which is that you dereference the result before you bind it, which doesn't look like the way you normally treat allocated storage. But these things aren't really allocated storage. And so the fact that it looks a little odd here might actually be a virtue. This is a style that you can adopt to inform the reader of this code that this thing isn't a conventional memory allocation. It's a memory mapping operation, which looks a lot like, and you can think of it a lot like that kind of storage allocation, but I'm binding a reference to it because I want the thing to look like an object. And so then you can manipulate the COM port like it's an object. You're disguising this memory map location to look like a properly constructed object. Next. Now, suppose there's more than one UART. The one that I just wrote has a hardwired address right there. What do you do about the addresses of the others? Well, that's a simple change. Next. What you can do is you can just add a parameter to the operator new, which specifies the UART number right there. And in this particular case, on my hardware, they are all at equally spaced addresses. So you can use a simple multiply there. You take that UART number times an offset, and actually that should have, in my examples, that shouldn't have been 1,000, it should have been 100. But you get the idea. Next. So now you can just do this. You can say COM0 is a UART, and it's the 0th UART, or a COM2 is UART 2. And this, again, the user of the UART class doesn't have to know the magic number of that address. It just says, I want the second UART, I want the third UART. You find the address at the right place for me and construct it. Now, there's a problem with this. The problem is it only works properly if the value is 0 through 3. Next. What do you do if the value is out of range? Something like that.
You validate the value that is
Yes.
structure inside the.
Now, you could do a runtime check, but it turns out you can do it at compile time. Very simple way to do it. Next, use an enumeration. Right? You use an enumerated type here, in which I just used the very original name 0123. And
With this enumeration, you even don't need this n type 0x1000. Each enum value could stand for a offset of each.
yes, I could make each one of these equal. I could put an equals here and specify exactly what that is. That would be a way to handle irregular spacing. So yeah, there are different ways to package this. But the critical thing is that instead of using an integer here, which would have to be valid range checked at runtime, I can use an enumeration type, and that will be checked at compile time. If I pass anything that's out of range, well, there are no other values. And anything else I do, I would have to use casting to defeat the type check. And yes, that would turn off the check. Hopefully a human being would catch that. It would be just obvious that there would be a cast expression in this call, and you'd say, why are you doing that? And you say, well, because I want to do something out of range. And then it becomes an indefensible position. Next. So this is what the syntax would look like right there. And that is nice and clean, I think, fairly easy to read, and can be statically checked. It means that no longer compiles, and I think that's a good thing. Next. So this was just my effort to illustrate how I think you can write some very nice, clean, thin wrappers to take things that normally look like stray integers and bits and stuff like that and wrap them up in a nice, tidy package. And the key is put your energy into writing declarations at the beginning, and then the use thereafter becomes much simpler. So you want to write declarations that model the hardware as precisely as possible. And when you do it well, you should see the payoff in that the code which uses these declarations will be much easier to work with. Next. I think that's it. Ta-da. Thank you all.
Yeah, so about the layout and the layout of the structs, you showed a way to statically assert that this doesn't break, but what to do when it breaks? If you port it to some architecture.
Oh, the question is, if I do get a static check which says that it is not standard layout, what do I do? Well, it would fail that check. First of all, is standard layout is a property that is portable?
Well, I was speaking about the
offset checks?
The offset checks, yes.
Oh, in the case of the offset checks, if you're compiling the code on one platform and everything seems to line up and it passes the checks, you take that same code to another platform and now it complains, it means that that compiler was inserting padding bytes or changing the alignment. And you're just going to have to do some experimenting to figure out, okay, what was the compiler doing? Let's look at the generated code at the offsets. You then have to look in your user documentation to find out, is there a facility like a pragma or an attribute that will allow me to pack the structure and then insert explicitly the padding that I need to insert to make it line up properly. And so there isn't really a portable solution to that. You'll wind up customizing that for each platform, and you might have to use a little bit of conditional compilation to package this to say, have an if-def that says if it's this platform, do it this way. If it's all other platforms, do it another way.
Can't you use this with reinterpreting this and applying the offsets to this keyword?
Oh, can you use the this keyword and reinterpret the offset? I don't believe so. No. Because, well, what you don't want to do is get into runtime calculations of the offsets of members. You want to make those compile time calculations. You're going to get better, tighter code. And more, letting the compiler do offset calculations is much more reliable than you trying to do them in an ad hoc fashion.
A quick question. The situation when you have two of those USART objects, one is a console and the other is a driver for some kind of motor, for example, and it's 2 a.m. at night and you're having a problem when you switch those USART in the implementation and you want to write I'm going on the console and start to the motor, but in fact you switch those and neither console is writing anything and the motor doesn't do anything. Is there a way to block a situation when two objects are mixed each other? I'm putting the wrong data to the motor and the wrong data to the console.
It sounds to me like that's just a programming logic error, that you've got somehow or another you meant to be using
one USART
one for
driving.
one purpose and you picked up the other one. Off the top of my head, I don't know a solution to that general problem. I mean, what I've been preaching about trying to turn runtime errors into compile time errors, I said it's an aspiration. You'll never get there because it doesn't really cover large categories of just logic errors. So what you can do with the techniques that I've been suggesting is that you can eliminate quite a number of just careless errors, things that can be caught by the type system, but a logic error of simply choosing the wrong device. I'm not sure offhand that I have a nice solution for that.
Okay, thanks.
Do we have any other questions?
There's one there.
Any particular advice in case we are dealing with device which accepts data in various endianness? Like for instance, one register accepts little endian value and one accepts and at the same time the other value is using the different endian and some kind of I mean, where would you put this endianness translation?
That's
I mean,
a very good
instance,
question.
would you, for instance, create some kind of class which does the byte swapping under the hood, and you have assignment operator overloaded properly, or you would advise something else, like for instance, if defs and various variants of classes with different layout in the fields? Okay,
you're basically addressing the problem of endianness.
Yeah.
Big endian versus little endian within some of the registers. Now, I have a question for you and actually for everybody. My experience has been that architectures tend to be uniformly big endian or little endian. Do any of you have this situation where it's like the architecture is little endian, but then one device has been done that way? That's the... Any other poor souls besides him? I'm just curious. This is how I learn, is to see how prevalent this problem is. So what I would say is there ever, I'd ask questions like, is there ever a reason to communicate with that register in its native way, or do you always want the byte swapping to be inherent when you talk to it? In other words, if you have an architecture which is dominantly big endian, but this one register which is little endian, is there ever a situation where you would want to still treat it little endian, where you want to send it little endian data? And if the answer is no, then I would put the byte swapping right in there to say, just disguise it to everybody else. Unless there is some major performance problem with doing it in there. It seems to me creating the illusion that that register is not a renegade is advantageous. But if you find that, oh, sometimes I do need to have a big endian write and a little endian write, then you have to separate that functionality out.
well, let's say that performance is not a problem, but pure convenience and being error prone.
Well, then I would say just write the interface functions for that device, for that particular register, so that the byte swapping handles behind the scenes to... I say, I want everything to look big endian, even though that register isn't. I'll let that class disguise that register to look like a big endian register, even though it isn't. I think that's the easiest to use correctly and hardest to use incorrectly.
Okay, any other questions that we might have?
Oh, way in the back.
Okay, we're waiting.
Hey,
for the
how about if you
microphone to get
compromise and come down? Yeah.
Thanks. You redefined the new operator. What about delete operator?
What about delete?
Yeah.
I typically don't. These are not things that you delete. I mean, but if there is a notion of shutdown, you know, many of these systems they're up and running and there isn't this idea of shutdown. But you could do it, you know, where the delete of that pointer has the effect of running a destructor, which may have the effect of configuring the device in a state so that it's no longer turned on. It's no longer talking to something external. And so I don't think there's any inherent reason why you couldn't do a delete. I just didn't, in my own work, that's something that I rarely confront, and I didn't have time to include it. But that's a good idea.
So you can use this new EQ delete syntax on the function to avoid. So every time the user will want to cut this function, it will.
You're saying use the equals delete in the declaration
Of delete.
of the delete function to say, no, you can't implement it. You can't delete that, yes.
Yeah.
And yes, if you want to prevent them from trying to do that, yes, that's a good way to defend against that.
There is any way to block creation more than one mapping. So, for example, I want to have only one UART 0 mapping in the whole system. So there's any way to, for example, compilation time check that I am creating only one UART mapping?
In other words, you want something like a singleton? Is that it? In other words, yeah, you want to make sure that there aren't multiple attempts to new UART 0. And you can use some of the classic techniques for wrapping that. But the thing you have to watch is that if you want to make sure that the mechanism for wrapping that doesn't disturb the standard layout. Instead, you'll use, you know, I think any of the classic singleton techniques as a way of making it so that new itself is not publicly accessible, and instead you give them an instance function and do it that way, something like that.
So again, let's thank Dan Zacks for this talk. Thank you.